Yeah, thanks. Thank you, Vesti. First of all, I would like to thank organizers for giving me opportunity to present here and for organizing this event. Yeah, I can't even imagine how hard it was to organize in the hybrid mode, but it seems so far everything goes smoothly. So thank you again. So I'm going to talk about a recent joint project together with Vesti, with Isola Apostolov, and with Jeffrey Streets. And about some of our prior work with Jeffrey Streets as well. So the title is Variational Approach to Generalized Kähler-Ricci Solitons, but let me actually start with something more fundamental probably. So with Kähler geometry. So if we start with a compact manifold, so let's pick on this manifold compatible Riemannian metric, which will denote G through this talk, and an integrable complex structure, which we denote I. Then this manifold is Kähler if the associated 2 form, which you get by plugging in I in one of the coordinates of your metric. So this form is closed. This is the definition of being Kähler. And in particular, automatically you define a cohomology class of your 2 forms. So this will be an element in the second cohomology of your manifold. And in this case, you can define a notion of a Kähler class. You can consider all possible Kähler structures. So usually you fix your manifold and you fix complex structure, and you look for all compatible Riemannian metrics which make it Kähler, or equivalently for all compatible closed 2 forms, which could be used to recover a metric. So this is a Kähler class, and thanks to the DDC lemma in Kähler geometry, this has a very nice equivalent description as follows. So you can consider the space of all functions modular constants, and you just add to your initial form omega DDC of your function. And as long as this 2 form is positive, definite, what you get is a Kähler metric. So in particular, what we see from this description that formally you can think of a tangent space of a Kähler class as a space of all smooth functions modular constants. And furthermore, if you fix any smooth function on your manifold, you can define at least infinitesimal variation of the Kähler structure in the direction prescribed by this function phi. You can basically multiply it by a very small number, and if this number is sufficiently small, you can ensure that this form is positive definite as long as omega was positive definite. Okay. So, what fundamental questions of Kähler geometry concern is essentially the study of these Kähler classes and distinguished members in them. So probably one of the most important question is to find distinguished metrics in a given class, and examples of these questions are the search for Calabi-Yau metrics, the search for constant scalar curvature Kähler metrics, so which were driving the research in this area for past many decades. Another type of questions would be to identify which manifolds admit some Kähler class with some distinguished special metrics. So these all related to questions of K-stability, the search of Einstein metrics on Panna manifolds, and minimal module program also can be looked at through the lens of this question. And furthermore, there is kind of a next level of looking at it, so maybe modular questions. So you ask yourself how your distinguished metric changes if you change your Kähler class. And this leads to the question of the generation of Calabi-Yau manifolds, collapsing fibrations, and yeah, many other exciting questions to this topic. So this is a very well established and developed field. What I'm going to talk about today is actually an attempt to set the scene for similar types of questions in a different geometric setting, in the setting of generalized Kähler geometry, so which I'm about to describe. So you can think of a Kähler structure on a manifold as a pair of operators. And these operators will be defined as the sum of tangent and cotangent bundle. So you can use your complex structure I and its dual to define a map from tangent plus cotangent to itself. And you likewise can use symplectic form to define a map endomorphism of the same space. And these endomorphisms, they identify several obvious conditions. So they both formally are complex structures, almost complex structures. They commute with each other. And if you denote by angle brackets the natural pairing which you have between vectors and covectors, then this symmetric form happens to be positive definite. So this interpretation of Kähler structures can be used as motivation for the definition of generalized Kähler structures. So I will give sort of a simple version of that, and then I will quite quickly switch to another description. But just to give you context, I would like to at least give this definition here. So in this form, this definition was given by Mark Gualtieri. And it says that generalized Kähler structure on a manifold M and on the sum of tangent and cotangent bundle is a pair of operators J1 and J2, satisfying the above conditions. So these sort of linear algebraic conditions. And on top of that, you need some integrability conditions. So in the Kähler case, these were conditions of I being integrable complex structure and omega being close to 4. So in general, this is formulated through eigen subbundle of operators J1 and J2 being involutive with respect to natural bracket on this bundle, which is an extension of the Lie bracket of vector fields. And this definition can be extended. It needs to be extended for our purposes to exact current algebroids. So this actually not direct sum of tangent and cotangent bundle, but rather an extension like this, where sort of these pieces are glued together using B transform. And this also defines these are classified by a class of in third cohomology up to equivalence. So this class, three cohomology class will be important for us, but specific definition will not, because again, quite quickly, I would like to switch to another interpretation of generalized Kähler structures through the language of bi-Hermitian geometry. So here it is. So that's this definition. Seemingly, it has nothing to do with what I've been describing so far, but in reality, it is equivalent. And this equivalence was established exactly by Gualtieri. So from the previous definition, he derived this equivalent notion of generalized Kähler structure. So we started with a smooth manifold M, and then so for us from now on, generalized Kähler structure consists of the following data. It is a Riemannian metric G. It is two compatible integrable complex structures I and J, so compatible with the metric, meaning that they are orthogonal transformations. Then given metric G and two compatible complex structures, you can cook up forms omega I and omega J. So perhaps I should have written it here. So it's as before, omega I is a two form which you obtain if you hook I inside G, and omega J likewise is a form which you obtain if you hook in J. And you have this twisted differential, which up to sign errors and conventions is twisting of the usual differential by extension of extension of complex structure acting on differential forms component wise. So the condition here is that these three forms, they are required to be opposite of each other. So these three forms opposite each other, and that you know this three form by H, and the next condition that these three forms, they are actually closed. So both of them are closed. So this is what we saw as flux, as I understand in the previous two talks by Anna Fina and by Jason Latte. But there it was sort of important and interesting to have non-trivial flux and H not being closed, while for us, we will consider only closed H. And in terms of the complex geometry, this is equivalent to the condition of metric G to be pluriclosed with respect to I and respect to J separately. So let's give several examples of these structures. Let's see how it works. So we started with generalized Kähler structures as generalization of Kähler structures. So obviously, we should see Kähler structures through this Hermitian definition as well. And indeed, if you start with a known as Kähler manifold, you can think of it as a generalized Kähler manifold by just taking J, this second complex structure, to be equal to I. So in this case, conditions 3 and 4, they are vacuous because H just identically 0, and the rest is satisfied, obviously. So any Kähler manifold is generalized Kähler in a trivial way. And actually, as well, you could have taken J to be negative I if you wanted to. So another example, more interesting from the point of view of generalized geometry and more interesting from the point of view of what we're going to discuss, is the case of hyperkähler manifolds. So you can take hyperkähler manifolds. So recall that this is a Riemannian manifold with a triple of Kähler complex structures I, J, and K satisfying quaternionic relations. So I composition with J equals K, etc. So any such hybrid Kähler manifold can be actually thought of as a generalized Kähler manifold in more than one way, in fact. So I, J, and K, they define an S2 worth of complex structures. So this triple define S2 worth of Kähler complex structures. And you can pick any two representatives of this two-dimensional sphere, and these will give you a generalized Kähler manifold. So this is genuinely different from the previous example, of course. It's still not super exciting because we are still on a Kähler background. So the manifold, the underlying manifold, if you forget about metric and keep only one complex structure, it's still a Kähler manifold, or manifold admitting a Kähler metric rather. So there is another construction which will give you actually a generally non-Kähler metric, but still a Kähler background. So this is so-called Joyce construction. At least this is how it was introduced in the literature by Apostolov, Gadushon, and Grancherov. If you start with a hyperkähler structure, so it will be a manifold, metric, and 3 compatible Kähler structures, which are each of them is separately Kähler, and they satisfy quaternionic relations. Then what you can do, you can consider a Hamiltonian diffeomorphism of M, Hamiltonian with respect to Kähler form omega k, the Kähler form of this third complex structure. And you can keep your first complex structure I, you can pull back the second complex structure J, and there is a way to appropriately modify your Riemannian metric G. So specifically, you do it by considering this quadratic form. So as long as this quadratic form is positive definite and defines a genuine Riemannian metric, the corresponding tuple M, G tilde, I, and the pullback of your complex structure J. So it is also a generalized Kähler structure. And why it is interesting compared to what we have seen, it will be genuinely non-Kähler in the sense that if you forget, for example, the second complex structure, this triple is non-Kähler in general. So the way to think about this construction, which will be useful for us later, is that what it gives us is a local action of an infinite dimensional group of Hamiltonian diffeomorphisms of the manifold. So this is an infinite dimensional group with a Lie algebra modeled on smooth functions modular constants. So this infinite dimensional group acts on the set of all generalized Kähler structures on your manifold M, and it actually preserves I. So that's why I put I here in this set. So this is generalized Kähler structures extending the prescribed complex structure I. So it's a new example. It is non-Kähler structure, but the manifold itself, if you forget about metric as well, is still Kähler. So as a complex manifold, it's still a manifold admitting Kähler metrics. So it's interesting to also find something else beyond this Kähler world, which we started with. And the following example will be actually important to us in what follows. Oops. So this is a key example of generalized Kähler structure on non-Kähler background, and this is an example of Hopf surfaces. So specifically, I recall the definition of a primary Hopf surface. You start with a two-dimensional complex plane. You remove the origin and you act on it by holomorphic contractions. So you pick up a holomorphic contraction and you act on the space by holomorphic contractions. So the quotient happens to be a compact smooth manifold, diffeomorphic to a product of a three sphere and a circle. And it inherits complex structure from the total space. And these happen to carry several important examples of generalized Kähler structures. I will mention two of them, and actually we'll study them in more details later. So first one, so it works actually in any situation where A is diagonalizable. It means that in appropriate coordinates on C2 minus the origin, you can pick coordinates Z1 and Z2, for which I is A is just diagonal matrix acting by linear contractions of the ambient space. So in this case, this operator A, it preserves the natural splitting of the tangent bundle which you have. So you have direction Z1, you have Z1 direction and you have Z2 direction. This directions they preserved by operator A. So they define a splitting of the tangent bundle on your Hopf surface, which allows you to define a second complex structure by keeping the structure on this component of the splitting and conjugating the complex structure on the second component. So it happens to be an integrable complex structure. And if you pick up a pluriclose metric compatible with the splitting, so for which the splitting is orthogonal, you will get a genuine generalized Kähler structure on the Hopf surface. And there are a lot of them because there are a lot of pluriclose metrics. So another example, which is more interesting and actually more important for what we're going to talk about. So I'll give you a specific geometric version of it. So there is a less explicit, which will appear later. So this is a very special case of diagonal of a primary Hopf surface and of a diagonal Hopf surface where matrix A is diagonalizable. So in this case, matrix A is a matrix just acting by contractions by a factor of 1/2. So such Hopf surface also admits a generalized Kähler structure and a very explicit one. So the metric which you have to take here is a conformally modified Euclidean matrix. You take Euclidean metric on C2 minus the origin, and you multiply it by conformal factors, so it will become invariant under this action. So it will become sort of a cylindrical metric on S3 cross R. Then once you quotient it by the action of your contraction, you will get a genuine metric on the Hopf surface itself. So that's as for the metric. For the complex structure, it's a bit more interesting. So the second complex structure, the way you cook up it, you pull back it by an evolution of C2 minus the origin. And this involution is a composition of the inversion of C2 minus the origin and a reflection in any plane. Actually, you can take any plane, complex plane through the origin and take reflection in it. So this will be the second complex structure, and it turns out, I mean, it's not obvious from the description which I just gave you, but it turns out that this collection of observers with the initial complex structure I, this metric G, and the second complex structure J, they together give you an example of generalized Kähler structure. And it's interesting because it's genuinely non-Kähler. Observers doesn't carry any Kähler metrics. So I will have also to describe some extra data which any generalized Kähler manifold carries with it. The most important for us for today will be the Poisson tensor sigma, real Poisson tensor sigma, which is essentially the commutator of complex structures I and J, where you lower one of the index using symmetric. And the more important feature of this sigma is actually is a real part of a holomorphic to zero Poisson tensor. So you can consider tensor which are called sigma I. It's actually a complex valued Poisson tensor, and it happens to be holomorphic of type 2,0. And likewise, the same works for complex structure J. So you can also define sigma J by the same fashion, It also will be J holomorphic this type, and also will be of type 2,0. Also underlying any generalized Kähler manifold, there are symplectic forms. So symplectic forms you can get by considering I plus or minus J, inverting this operator, and again using G to turn it into a two form. So this is not always defined, right? There is no guarantee I plus J or my I minus J is invertible. But whenever it is invertible, this will be a symplectic form, at least locally. So we will need a couple of special cases of generalized Kähler structures. So one will be when sigma is actually global invertible, such structures will be called non-degenerate. And another when it is generically invertible, or equivalently, it turns out it's enough to require that sigma is invertible at least at one point. So if it is the case, then the structure will be called log non-degenerate. Final piece of notation or final notions which we will need, the notions of odd or even generalized Kähler structures, which makes sense if the dimension of your manifold is divisible by 4. We'll be seeing only in the case when dimension of your manifold is exactly 4. So the generalized Kähler structure is even or odd, depending on whether I and J induce the same orientation on your tangent bundle or they induce opposite orientations on your tangent bundle. So for instance, in the example above with Hopf surfaces, these are odd generalized Kähler structures. So here orientation is different, defined by I and J. And this is an even generalized Kähler structure. Okay. And again, final remark that you can take generalized Kähler structure and you can forget about one of the complex structures I or J. You can remove it, and doing so, you will reduce the structure to a pluriclosed complex manifold. So you have actually two underlying pluriclosed manifolds, MGI and MGJ, and as any Hermitian manifold, they also will have underlying Lie 1 forms, which are recall defined as follows. Again, these Lie forms will be somewhat important later. So we saw notions of balanced manifolds today in the morning. So for balanced manifolds, these are actually 0 because your omega is closed, but in general it is not. And in our case, it will not be balanced. Any questions so far?
We're fine.
Okay. So now I'm going to talk a bit about the formation of generalized Kähler structures. So we start with a manifold generalized Kähler structure, again in this bi-Hermitian language, and we fix underlying Poisson tensor sigma. So it turns out that very similarly to the Kähler case, you have a procedure to deform a given generalized Kähler structure. So yeah, I included here a bunch of names because it appears the different versions of it appear in many contexts. So as I have said, Apostle of Godish and Goncharov, they introduced, attributed it to Joyce. So there is this notion was introduced by Gualtieri in the so-called symplectic type case, and also was studied by Hitchin on Del Pezzo surfaces. And this notion, which I'm going to describe in this form, was described by Gibson and Streets. So you start with a family of smooth potentials, and you consider the corresponding sigma Hamiltonian vector fields. So you hook up d of Vt into your Poisson tensor. So you get a smooth vector field whose flow preserves Poisson tensor. So what you can do then, you can consider the following one parameter family of matrix and complex structures. So complex structure J actually will be fixed. So J doesn't change here in time. I changes just by the flow of the corresponding Hamiltonian diffeomorphism. And metric G changes by more complicated expression. But the point here that along this flow, generalized Kähler condition preserves, so you get the flow of generalized Kähler structures as long as your metric remains positive. And probably it's worth noting that one of your complex structures doesn't change. Another complex structure flows by Hamiltonian diffeomorphisms, and your underlying Poisson tensor actually also doesn't change. So both complex structure, one of the complex structures, and Poisson tensor, real Poisson tensor, do not change. The other ingredients of a generalized Kähler structure do change in a very explicit way. So interestingly, this exactly recovers the Joyce deformation. If you start with a Haber-Kähler structure, if you start with a Haber-Kähler structure, this tensor sigma is actually what we before saw as omega k, this Kähler form associated with the third Kähler structure, sort of complex structure. And this is exactly what that Joyce deformation gives you if you write it down carefully. And maybe a little bit more surprising, but actually the same notion, the same procedure recovers the notion of deformation in a given Kähler class. So if you forget about generalized Kähler geometry, if you just think about Kähler geometry, changing your Kähler class also follows the same procedure. So in that case, if you remember in the Kähler case, I equals J. So your symplectic form is actually trivial. So sigma is 0. It means that you don't have any vector field. Your vector field is also identically 0. And all modification happens here. And this is exactly adding DDC of a function to your Kähler class. All right, so once we have a notion of deformation of generalized Kähler structure, we can make sense of a generalized Kähler class. So maybe let me first reiterate a bit of what this sigma Hamiltonian flow construction actually does. So the useful way to think about it is to think about it as an action of an infinite dimensional Lie group, which are called H sigma, with the Lie algebra modeled on the same space, on the space of smooth functions modular constants, and with a bracket given by the Poisson bracket. So this infinite dimensional Lie group with this Lie algebra acts on the space of all generalized Kähler structures in your manifold. And Gibbons and Streets, they suggested the following notion: generalized Kähler class is just an orbit of this action. So you start with some base point, let's call them 0. So M0 is some starting generalized Kähler structure in your manifold. You act by the flow construction. So you act by this group, and the orbit of this group is what we will call generalized Kähler class. And again, maybe I should reiterate, this is a local action. So we act and consider those structures for which metric happens to be actually positive definite. And again, in a given generalized Kähler class, we have fixed complex structure and fixed Poisson structure. So once we have a notion of generalized Kähler structure and generalized Kähler class, so we can ask the same type of questions as we did in Kähler settings. So we might want to find distinguished metric in a given class. We might be wondering which manifolds, complex manifolds, or even Poisson complex manifolds, which of those admits distinguished metrics in some generalized Kähler class, if there exist generalized Kähler structures. And again, you can as well study variations of distinguished metric as you change your generalized Kähler class. So to formalize some of these questions and to make them similar to what people study in Kähler world, we need to generalize two notions. We need to generalize the notion of a Ricci curvature, because this is how normally distinguished metrics defined in Kähler geometry, and it's also will be helpful to generalize the notion of a scalar curvature. So over the last decade, so this has been done actually, both of these parts in the works of Garcia Fernandez, Streets, and Tian in different combinations. So they studied a lot generalized Ricci curvature, and Boulanger and Goto they studied scalar curvature, introduced the notion of a scalar curvature of a generalized Kähler manifold. Maybe I should say that they both did it here viewing scalar curvature as a moment map. So that was actually the key for this construction. So the purpose of this talk, what I'm going to discuss, is actually a way to focus on this question. I'm going to focus on studying distinguished metrics in a given generalized Kähler class. And specifically, the type of metrics which we're going to study are generalized Kähler-Ricci Solitons, which I will discuss, define on the next slide. So generalized Kähler-Ricci Soliton is a system of equation on a generalized Kähler manifold and a smooth potential, Soliton potential F. So we will say that this collection, this data, is a gradient steady Ricci Soliton, or generalized Kähler-Ricci Soliton, if this data satisfies the following two equations. So this is just the usual Ricci curvature. This is a symmetric contraction of 3-form H with itself, and this is Hessian of smooth potential F. And yeah, this is just a sort of certain codifferential, weighted codifferential of 3-form H. So let's look for a second at this equation. If H is identically 0, so this equation is vacuous, it disappears, this term disappears, and all what is left is actually just the standard usual gradient steady Kähler-Ricci Soliton equation, again, which have been studied, of course, a lot. And if you further impose that function f is 0, or rather constant, you don't have any of these terms here, and your only equation is being Ricci flat and Kähler, which is equivalent to the Calabi-Yau equation. So to give you one example of the solution, which is not Calabi-Yau, you can turn back to this even generalized Kähler structure on Hopf surface. So where you identify it under the contractions by a factor of 2. And you take this conformally modified Euclidean metric, then this structure is a genuine generalized Kähler-Ricci Soliton. It's not super general though, because here function f, your Soliton function, is actually constant. But again, it's still something new compared to what we have seen in the Kähler world. So maybe let me give you some non-existence result about solitons, or at least non-existence of interesting solitons. So if you start with a compact generalized Kähler-Ricci Soliton, gradient steady, the one which I defined in the previous slide, and if you assume that I plus j is invertible, then necessarily h is 0, f is constant, and you really are on a Calabi-Yau background. So how one proves it? So the key to prove it, that a plus j being invertible, means that you have this special sympathetic form, as I mentioned. And one of the consequences of generalized Kähler condition is that if you have such a symplectic form, that you can actually find a primitive for your closed form H. So your closed form H has to be zero in cohomology and has to admit a very explicit primitive B. So here I have written what this primitive is. And then just considering the second equation of the system, Soliton system, so this equation about free form H, and while integrating by part once, you immediately get that the weighted derivative of norm of H is zero. So H has to vanish, and since H has to vanish, you're really a Kähler-Ricci soliton, and all compact Kähler-Ricci soliton must be just Ricci flat. So nothing interesting occurs here, nothing beyond we have seen already. So this proposition shows that if we are after something new, after sort of non-trivial generalized Kähler-Ricci solitons, then we have to allow I plus j to be invertible, and likewise we have to allow I minus j to be, sorry, non-invertible, at least somewhere on M. And that will be assumption from now on for us, but we relax it as little as possible. So we relax invertibility as little as possible. So sorry, I should. Yeah, so we really assume that the invertible at some point x. So there is one point x where these two operators are invertible, but they both can degenerate somewhere on your manifold M. So in this case, actually what happens is they will be invertible on an open dense set of your manifold, and the locus where they are non-invertible, it will be analytic. The reason is, or at least it will be contained in the proper analytic subset. The reason is why it will be contained in the proper analytic subset, because the locus where I plus j and I minus j are non-invertible, it's contained in the locus where Poisson tensor is non-invertible, because Poisson tensor contains just the product of these two operators. And whenever Poisson tensor is non-invertible, this locus is actually part of the canonical divisor either of Mi or Mj. So these are equivalent here in this setting. So under our assumptions, therefore, we still have the symplectic forms, but they are now defined not entirely on your manifold M, but on proper open dense subset of your manifold. So it happens that similarly to the Kähler case, you can cook up Peeling holomorphic vector fields from the soliton data. And that's the content of the next proposition. If you start with a lockdown degenerate generalized Kähler-Ricci soliton, and you consider these two vector fields, so these are gradients of f combined, linearly combined with Lie vector fields, dual of Lie forms, and then multiplying by I or j. Yeah, I just got a message that my battery running low. Again, if it gets too low, I will plug in again. So far, I think we can go on. So it happens that these two vector fields, yet again, it's a formal consequence of the Soliton equation, that they are both Kähler, they are I and j holomorphic, and they commute with each other. So there is actually a lot of structure immediately implied by the Soliton equations. And if you drop Soliton equation, but still consider these two special vector fields, that what you can observe that their sum and their difference are respectively f plus or minus Hamiltonian with smooth potentials defined on this open set u plus and u minus. And these potentials, they can be chosen so that you have this identity of the volume forms. So this is point-wise identity of the volume forms. Maybe I'll make a little comment about this identity. So this form is globally defined. So this volume form, which is defined everywhere on M. While this form, a priori, it's only makes sense on U plus or U minus, because sympathetic form only defined there, and symplectic potential psi also defined on this open dense subset. So in the implicit consequence of this identity, that the form on the left-hand side, which was defined on the part of M, actually extends smoothly to the entire manifold. So it turns out that observations which appear here can be used to get characterization of a soliton. And that's what I'm going to discuss. So that's kind of important proposition for what to follow. Generalized Kähler manifold, which is log degenerate, that's our input. And we also pick two vector fields, which kind of mimics the behavior of vector fields, which I just mentioned. So we pick vector fields xi and xj, which preserve all the structure I, j, and metric g, so that they are Hamiltonian. Xi plus or minus xj are f plus or f minus Hamiltonian with corresponding smooth potentials. And the volume forms extend smoothly to the entire manifold. And so this is actually the key. These volume forms, they are equal to each other. So if it happens, if these two volume forms equal to each other, then actually your structure is a generalized Kähler-Ricci soliton with appropriately chosen smooth potential f. So it's a quite amazing interpretation of the Soliton equation in my taste, at least. Instead of some system of equation, you really reduce everything to one scalar essential equation, identity of volume forms. And identity of volume forms is something very well known and appreciated in Kähler geometry, because this is really the source of all applications of Monge-Ampère equations in Kähler geometry, because this is a way you can interpret Kähler-Einstein or Kähler-Ricci Soliton equations in Kähler geometry. So now we have an analog of this in generalized Kähler geometry as well. Again, at least under some assumptions. So whether we can drop them or not, it's another question. So our next goal is to relate this interpretation of solitons to the Hamiltonian flow construction. So maybe I'll just go briefly over that. So as a motivation, the studying Kähler-Einstein metrics, Aban in 1980s introduced a functional in Kähler setting on a given Kähler class. And this functional is defined by integrating certain one form along the Kähler class. So, okay, sorry, I probably should plug in my my iPad. Sorry, give me 10 seconds. Let's resume. Are there any questions at this moment? All right, so yeah, let's move on. So Aban introduced this functional on the Kähler class in the attempt to describe Kähler-Einstein metric, studying Kähler-Einstein metric, and this is just an integral of certain one form over the generalized Kähler class. So you have to check that to integrate this one form, you need to check that it's closed, so that you get something independent of the path of integration, which he did, and so it happened to be useful. And there are many other functionals in Kähler geometry. It's actually like the main source of new examples and new results in Kähler geometry now is like the smart choice of functionals. So there are, for instance, certain weighted modifications of this functional as well. So that's what we're going to try to do in generalized Kähler setting. So let me set things up. So we start with a compact log non-degenerate manifold. We pick up two commuting vector fields, preserving your structure, preserving I, j, and j. So they will be generating some torus in the isometry group. So we fix this torus G. And we now will be considering not actually the generalized Kähler class, which we defined above. We'll be considering G invariant generalized Kähler class. And by G invariant, I mean the class which you obtain flowing only along Hamiltonian potentials, which are invariant under this choice of group G. So that will be important for us. So that's the notion of a generalized Kähler class, which is G invariant. So it's obviously smaller than the full generalized Kähler class. And you impose certain normalization on the potentials. So as above, you assume that xi plus or minus xj are f plus or minus Hamiltonian. You choose potentials which are normalized in a certain way, and you assume that these volume forms extend to smooth volume forms over M. And in this case, with this data, we define a one form on the G-invariant generalized Kähler class by this formula. So we integrate the difference between these two volume forms multiplied by phi over your manifold. And the key proposition, the heart of why the method works, is that this one form mu happens to be closed. And being closed, you can integrate it over contractible path. And if you do that, if you integrate this one form on a generalized Kähler class along all path, what you get is the following object. So existence of this object, I will formulate it as a theorem. So you get a functional on a G-invariant, on the universal cover of a G-invariant generalized Kähler class. You have to do universal cover here because you don't know much about the topology of the space. In Kähler case, it's contractible. In general, it is not. And we actually have very little understanding of what it is. So formally, this functional will be defined on the universal cover of this class. So it is 0 at the given base point, and the variation of this functional is exactly given by the one form defined here. And now using the variational characterization, using the Monge-Appert characterization of solitons, we now can say that structure in this Kähler class is a gradient steady generalized Kähler-Ricci soliton with underlying fields xi and xj, even only if it is a critical point of this function. So this is a variational characterization of solitons. And maybe I should make these remarks in a special case where xi and xj are 0, and in this case necessarily Poisson tensor is invertible, so this is non-degenerate setting. So in this assumption, the functional was discovered by Apostolov and Streets. So in this case, you don't need to put any weights here, but the easier part that in this case f plus and f minus are already globally defined, which is not the case for us. Okay. Just to give a couple of immediate consequences of the existence of this functional, let me state rigidity of solitons. So if you have a one parameter family of solitons in a fixed in G-invariant generalized Kähler class, then immediately you can conclude that this has to be rigid. So this family has to be constant, and this follows immediately from the second variation of the functional. Again, assuming that you have solitons along your path. Any questions so far?
Fine.
Okay. So let's move on. Yeah, I took a bit more time than I intended to, but yeah, let me discuss here one specific application which we have of all this theory, which in itself kind of a nice conclusive result about existence of generalized Kähler structures and solitons on surfaces. So let's recall that primary Hopf surface is a quotient of C2 minus the origin by contractions, and we have specifically subclass of diagonal primary surfaces. This is a case where A can be taken a diagonal matrix with appropriate choice of coordinates on C2 minus the origin. And a secondary Hopf surface is a finite holomorphic quotient of a primary surface. Hopf surface. And you might ask, okay, which Hopf surfaces admit some generalized Kähler structure? And if you know the answer to that, you might ask which Hopf surfaces admit generalized Kähler-Ricci soliton. And if you know that, you might ask, what about uniqueness? Are they unique or not? If they're not unique, then up to what equivalence they might be unique. And these questions happen to be easier to approach and study having the function which I discuss at hand. I'll first discuss briefly the odd generalized Kähler structures on Hopf surfaces. So recall it's odd if R and J induce opposite orientations. And Apostolov and Gualtieri actually proved that Hopf surface admits an odd generalized Kähler structure if on unleaf it is a possibly trivial quotient of a diagonal Hopf surface by a cyclic group acting via multiplication by roots of unity on the components, on the coordinates. So this action is written on C2 minus the origin, but it obviously descends to the action on the Hopf surface itself. So what follows from our prior results with Jeff Streets and from some careful analysis in our recent paper with Vesti and Jeff is that if you take a Hopf surface and you assume that it admits an odd GK structure, then it actually admits an odd soliton. So all these examples that admit odd solitons, they were essentially constructed in our paper with Jeff in a diagonal case, and then it requires a bit of work to understand the uniqueness. So that's what was carefully done in our last paper. So the conclusion is that such solitons are unique up to scaling, action of the automorphism group, and possibly swapping J and negative J. That's the only flexibility which you have. So the key idea here is that any odd generalized Kähler structure defines a holomorphic splitting, and studying carefully the action of the automorphism group on the space of possible splitting and invoking some, rather straightforward maximum principle, it was possible to deduce the uniqueness here. So I don't want to focus too much on it because this is not where functional plays role. So functional plays role if you want to study even structures. So if you have an even structure on a Hopf surface, then it is necessarily log non-degenerate. So this Poisson tensor is generically invertible. And it's a real part of a holomorphic Poisson tensor. When the zeros of this Poisson tensor, it's trivially a canonical divisor of a Hopf surface. And it happens that this canonical divisor must be disconnected. It must be a disjoint union of the locus where I equals J and locus where I equals negative J. So keeping in mind that, so this actually happens to be an important restriction, having a disconnected canonical divisor. You can actually classify which Hopf surfaces admit some even generalized Kähler structure. And it happens that this is the same exactly list as in the result of Apostolov and Gualtieri. So these are cyclic quotients of diagonal Hopf surfaces. And again, to prove this, to prove non-existence on the other ones, you need to understand which one admits canonical divisors with disconnected zero divisor, and to understand the automorphism group of this divisor. And to get the existence, so why there exists a generalized Kähler structure on any of those, it's actually a bit tricky, and I don't know an easy argument. The argument which we end up having is actually constructing solitons right away. So instead of constructing some generalized Kähler structures on Hopf surfaces, we actually know already that there exist solitons, and this is an explicit construction with streets. So we prove that any diagonal Hopf surface admits an even soliton, and the way it works, that we explicitly constructed it in the maximally symmetric ansatz. So if you put a maximal symmetry assumption, this is a maximal compact subgroup in the automorphism group. So if you impose this symmetry, then the Soliton equation reduces to ODE, which you can solve explicitly, and solving ODE actually gives you also immediately uniqueness under symmetry assumption. So this is existence on diagonal Hopf surfaces, and it's easy to see that they all descend to this finite cyclic quotients. So what remains to figure out is the uniqueness in general, not necessarily with mass symmetry assumption, and uniqueness on secondary Hopf surface on this finite quotients. So maybe I'll briefly tell you the idea. So again, as I mentioned, we already know uniqueness of even solitons if you impose maximal symmetry assumption. So for a fixed subgroup in the automorphism group. So the key is to get the a priori symmetry of a generalized Kähler-Ricci soliton. So you start with an even soliton on Hopf surface, and you want to prove that it must be symmetric without any other a priori knowledge of that. So if we remember our characterization of local degenerate solitons, we already have two-dimensional symmetry. We already have two commuting vector fields, which preserves the entire structure. And it's not that hard. It has to be done, but it's not that hard to see that these are non-linearly independent generically. So you already have two-dimensional symmetry, which has to a priori has to preserve your soliton. So to finish the job, we need to find the third vector field preserving the soliton. So if we somehow can prove that, then we'll be done. So how we do that? So we observed that if you start with generalized Kähler-Ricci soliton, even generalized Kähler-Ricci soliton on a Hopf surface, then in appropriate coordinates, your Poisson tensor sigma I can be chosen a complex multiple of this sort of standard one. And with this knowledge, you can find an explicit vector field which preserves or commutes with xi and xj, which preserves this Poisson tensor, and which doesn't have global Hamiltonian potential, but it has Hamiltonian potential with logarithmic singularities along the loci where zi equals 0. So it will be smooth everywhere except for this loci, and along this loci it will have logarithmic singularity. So you can consider symmetrically M with respect to the second complex structure, and by result of Kadeira, it also has to be a diagonal Hopf surface, and we can find an analogous vector field for this second Hopf surface. And now the key, what we actually did, we proved that these two vector fields, they must be the same. They must be coincide, which will give you a vector field which preserves the entire structure. And the key in this argument is the following lemma, which is pretty general. If you have a compact Lochner-degenerate gradient steady soliton, again, you take G to be a group generated by soliton vector fields, so it's a torus in the automorphism group. And you have two vector fields computing with this group G. They both preserve your Poisson tensor sigma, but they are also respectively I holomorphic and J holomorphic. And this is the key, their difference is Hamiltonian. So neither of them is Hamiltonian, they just preserve sigma, but their difference is Hamiltonian. So if it is the case, then they must coincide with each other. So how do I apply this this lemma? Well, we applied precisely to vector fields yi and yj, verifying that even though they have logarithmic singularity along zi equals 0, when you take the difference of these two vector fields, the logarithmic singularity cancels out. So it cancels out, and the difference happens to be, again, a priori Hamiltonian vector field. So this lemma would imply what we actually want. And to prove this lemma, so this is exactly where J functional enters the picture. So this is just a lemma restated. So to prove it is to observe that the flow of yi, so you can flow by diffeomorphisms generated by vector field yi. So since it's a diffeomorphism, it obviously preserves soliton equation, but it also happens to be equivalent to the flow construction. So you have flow construction, sigma Hamiltonian flow construction, which preserves Soliton condition. By rigidity, this flow construction has to be trivial, which forces vector fields yi and yj to match each other. And this is exactly this third vector field on Hopf surface, which preserves a priori any soliton. So from here, we can invoke our result with Geoff Streets and conclude that there is uniqueness on diagonal surfaces, Hopf surfaces. So yeah, it remains to figure out what happens with secondary Hopf surfaces. It's a little bit of analysis of automorphism group, but here's the conclusion that that any possibly trivial quotient, cyclic quotient of a diagonal Hopf surface admits an even. So that's what we prove now. Odd, that's what I explained before. Generalized Kähler-Soliton, and this soliton is unique up to scaling, action of the automorphism group, and possibly swapping J and negative J. And this theorem is actually can be used to sort of completely finish the classification of compact gradient steady solitons in dimension 4. So these are either Kähler-Calabi-Yau manifolds or odd/even solitons on Hopf surfaces, which we constructed and proved uniqueness here. So yeah, I'm a bit over time. Maybe I'll just leave kind of further questions for the directions over here. So type of questions which we saw here, which I find very interesting, is existence of generalized Kähler structures and existence of solitons in general. So you are given a manifold, complex manifold. Assuming you know that it admits some Fourier closed metric. So it seems like a general difficult and interesting question to understand whether this structure is a part of generalized Kähler structure. And likewise, you might start with a manifold complex structure and holomorphic Poisson tensor. And again, you might ask, can it be upgraded to a generalized Kähler structure anyway, or to generalized Kähler soliton maybe? And these all questions, they of course also related to the questions about the structure of generalized Kähler class of a given class and the structure of like the moduli of Kähler classes. So how those look like. So these questions are still very little understood, and these are definitely the exciting directions which hopefully could be approached with understanding canonical metrics in the respective generalized Kähler classes. Yeah, sorry for going over time a bit. I'll stop here.
Thank you very much. So are there questions from the room? Yes, Todd?
Is there so there was a lot of information in this. I'm trying to get something to take away. So one of the conclusions is that if you have a generalized steady, generalized Kähler-Ricci soliton, then the first Chern class vanishes, right? So is there a quick proof of that fact without using a lot of classification?
Yeah, there is. It's actually because it can be represented as a vanishing of the Bismuth-Ricci curvature of the homology class of the Bismuth-Ricci curvature.
Thanks.
Other questions? So perhaps are there some questions from the Zoom room?
I have a question, which is the following. Is there a candidate for an analog of the Scalar soliton?
Yeah, that's a very good question. Yeah, actually, so Scalar soliton is a complete soliton, right? Yeah. So you might ask what are complete solitons here, and it's absolutely exciting and interesting question. There are many examples of those, so there is no one answer. So actually, we have a joint work with Geoff Streets, where we constructed a lot of complete solitons, and this is essentially analogous to Gibbons-Hawking construction of Ricci flat manifolds with S1 symmetry. Sorry, hyperkähler manifolds with S1 symmetry. So the answer probably there is no one single analog. There are many examples, and they definitely they definitely play a similar role in applications of this story. But the whole story is richer and more complex than just one cigar soliton. Hope it makes sense.
Yeah, thank you.
Questions? Perhaps it's time to thank the speaker again.